In this lecture, we are going to study another synchronization primitive between threads called condition variables. So we've seen one type of synchronization between threads, which is locks, right? If threads need mutual exclusion, if we require that only one thread is executing at a time, then we will use locks. But there's also another common pattern that is required when multiple threads interact, which is that of waiting and signaling. That is, one thread might want another thread to finish some job and only then it will run, right? So this thread has to finish and then it has to signal, and this thread will wait and then run at this point, right? So for such kind of synchronization, we need another technique, right? So you could of course simply do busy waiting, right? This thread could set some variable after it's done, and this thread could simply just busily wait on that variable, but that is very inefficient. So instead, most operating systems have a synchronization primitive that is called condition variables, which gives you this technique gives you the ability to wait and signal, right? So the different operating systems call the synchronization primitive by different names, but we are going to go with the name condition variables, which is what is used in the pthreads library in Linux. So what is a condition variable? Condition variable is a queue into which a thread can put itself into for waiting. So suppose there is a certain condition that needs to be true, right? So one thread can say, it can check that condition. If the condition is false, it can simply put itself into a queue, right? And it can simply wait in that queue. And when another thread makes that condition queue, it can wake up the waiting thread. It can call the conditional variable and say wake up, at which point this thread that is waiting is going to get woken up, right? So a condition variable is a way for threads to wait and wake up. So pthreads provides conditional variables, and the operating system also has similar functionality for kernel threads. So sometimes a process in kernel mode might want to wait for another event, another process might want to signal it. For all such things, the operating system also has something like conditional variables for its internal consumption, right? So on a conditional variable, you can have two kinds of signaling. A simple signal can wake up just one thread, the first thread, or a random thread. Different implementations do different things. You can also have something like a signal broadcast, which wakes up all threads that are waiting on the condition. Okay, so let's see a simple example of code written using the pthread conditional variables, right? So here, this is what the example is trying to do. There's a parent, there is a child, and the parent wants to wait for the child. So once the child executes, then that is when the parent wants to continue execution, right? So there needs to be a signaling that happens between the parent and the child. Okay, so how is this done? So here is your main parent process. It creates a thread, it creates a child thread, and this child thread runs this function child here, and the parent calls this function join. What does this function join do? This join basically checks, is the child done? Otherwise it will wait, right? So you have a pthread conditional variable declared here, and you have this common variable done here. So what is the parent doing? The parent thread is waiting. It checks if done is 0, that is the child is not yet done. The parent will simply wait. It will call wait on this conditional variable. At this point, the parent thread goes to sleep. And when the child runs, right, the child runs, and when it calls this exit function, when the child is finished, it will set this done to 1, and it will call signal on the condition variable. So when the signal on the condition variable is called, that is when the parent thread is woken up and the parent thread continues its execution. So when you run this code, what happens? This printf statement goes first, the child prints child, and then this printf statement goes next. The parent will print whatever its stuff that it prints here. parent end. That will be printed after the child runs. Okay. So this happens no matter which way the operating system scheduler schedules threads, right? So sometimes the child thread could get scheduled first, sometimes the parent thread could get scheduled first, no matter what happens. So if the parent thread runs first, then it's going to wait. And if the child thread runs first, then the parent thread will simply check this condition, realize done is, the child has run, and it will not wait, and it will simply go ahead and execute. So this ordering of child first, parent next is guaranteed no matter what the operating system scheduler does, right? That is what conditional variables are used for, to ensure some kind of ordering, some kind of method to the madness of the operating system scheduler, right? So why do you have to check condition here in the parent? The parent shouldn't by default always sleep, right? The parent should sleep only if the child has not yet run. But if the child has run and if done is already 1, then the parent need not wait. It can simply go ahead and execute, right? So in all condition variables, before you wait, it's a good idea to check the condition. And only if you find that the condition is not true, then you will go to sleep. Because if you sleep, even if the condition is true, then nobody is going to wake you up, right? Because the wake up call, the child has already run. The signal has already happened. Okay. So we should always check condition before calling wait. Otherwise, if you always wait, then if the child has already run, has sent a signal, saw that nobody was sleeping, and then you come back and sleep again, nobody is going to wake you up. Okay. So check the condition and then wait. And also there's another subtle thing here. It would have been enough if you simply check the condition in an if loop, right? You can simply say if done is 0, then wait. So why do you check the condition in a while loop, right? Because this is sort of a subtle point and it is just good programming practice, because sometimes some library implementations may cause a spurious wake up. You might be woken up even if the condition is false, right? So to avoid such cases, so instead of doing this if condition wait, so if you do this, when you return from this wait, ideally you should return from the wait only when the condition is true. But sometimes you can return from the wait even if the condition is false. In such cases, to avoid such things, you use a while loop, so that once you wake up from the wait, you go back once again, just make sure the condition is true and then go ahead and execute, right? So this is good programming practice. So this is standard structure of code when using condition variables. You check on a condition in a while loop, and if the condition is false, you sleep, and somebody else will make the condition true and signal, and at that point you'll get woken up and you'll continue execution. So if you would have noticed, there's also another subtle point that a lock is held, right? So here there was also a mutex that we didn't talk about much, but there is a lock that is held and a lock that is given to the wait function, and the lock is once again held when you're signaling also. So what is a lock doing here, right? There's no shared variable counter updation and all of that. So why do we need a lock? So what if, for example, what if you just done this? The parent, if done is 0, this can also be a while loop, whatever. So check the condition and simply wait, and the child sets the condition and signals. So what happens if you don't hold a lock? So again here you can have a race condition even in this sleeping waking up process. Why? What is the race condition? Suppose the parent checks this condition. The parent runs first, it checks this condition, it sees that the child has not run, and it decides to sleep. Once the decision to sleep has been made, but just before it sleeps, at this point the parent is interrupted, right? The parent has not slept yet, but it has decided to sleep, right? It has decided to sleep and it gets interrupted. Now the child runs at exactly that unfortunate moment. This is the parent code and this is the child code, and the parent is interrupted. The child runs, it sets done equal to 1. It signals the condition variable, but is anybody woken up? No, because the parent has not slept yet, right? Therefore, the child signals, but that signal doesn't do anything and the child finishes. And now you come back to the parent. And now the parent has already decided to sleep, right? It's already about to execute this code. So it will go ahead, go to sleep. And now what has happened? Who will wake up the parent? Nobody will wake up the parent because the child has already said signal. It's done. So now the parent will sleep forever, right? So this is a bad thing to happen. So what went wrong? You do not want to be interrupted here, right? This is a very bad time to be interrupted. Once you've decided to sleep, you must sleep, right? These two lines should happen atomically, and that is why you need a lock. So you hold a lock here before you check the condition, and you give the lock to this variable, to the condition variable function, and the wait function releases the lock after control is taken away from the parent, just before putting the thread to sleep. Okay, so that you should never sleep with a lock, right? You can't just hold a lock and go to sleep. That is bad, because then we require that the child also takes the lock before it calls signal, right? So you hold a lock, you decide to sleep, you put yourself in that queue, and then the pthreads library will release the lock. And after it does that, then the child can signal. So either the signal happens before the parent sleeps or after the parent sleeps, but not during the parent deciding to sleep, right? So this process of going to sleep and waking up must also happen atomically, which is why you need a lock. Otherwise, you're going to have race conditions. Right? So the next example we're going to see with conditional variables is what is called a producer-consumer problem. Right? So this is a common pattern in multi-threaded programs. So what is a producer-consumer problem? You have multiple threads. Say one thread is the producer, another thread is the consumer, and then they have a shared buffer between them. Right? So the producer thread keeps on producing items in the buffer, and the consumer thread keeps on consuming items from the same shared buffer. Right? And here, of course, you need mutual exclusion on the buffer, right? You don't want concurrent access to the buffer. But you also need some kind of signaling. For example, if the buffer is full, the parent should sleep. And once the consumer consumes something, it should wake the parent up. Similarly, if the buffer is empty, the consumer thread should wait. Once the producer produces something, the consumer can get woken up. So you need some kind of signaling between these threads, and that is achieved with condition variables. That is, condition variables is one way to achieve that. And this is a very common pattern, this producer-consumer situation. For example, you have a multi-threaded web server, right? So one thread keeps reading requests from the network, putting it in the queue, and the other thread keeps processing these requests. So anytime multiple threads are cooperating to do some task together, you're going to have a producer-consumer kind of situation where one thread does something, hands over some data to the other thread consumes that data. Okay, so you can have one or more producer threads, you can have one or more consumer threads, and you have a shared buffer of a certain size. So we are going to see how you can write this code with condition variables. So here is simple version of the code. You have two condition variables, empty and filled, and you of course have a mutex, a lock to protect the process of sleeping and waiting and waking up, right? So let's look at the producer code first, right? The producer code acquires a lock and it checks if the number of items in the list is equal to a maximum value. So if the list is full, right? If you've reached the end of the list, then the producer must wait. It waits on this empty condition variable. And who signals this condition variable? When the consumer consumes an item. So the producer is doing a put here, the consumer is doing a get. When the consumer consumes this item, then the consumer signals this empty condition variable, right? So whenever you're writing code with condition variables, always match the wait and signal statements, right? You should never have a wait statement without a corresponding signal, because otherwise you're going to be sleeping forever. So the producer sleeps if you have filled up the buffer, there's no more space to produce, and the consumer, after consuming some item, now that there is empty space, signals this condition variable. Similarly, the consumer must wait. If the buffer is empty, if there's nothing to consume, then the consumer waits on a condition variable. And who signals this condition variable? The producer. Once the producer has produced something, the producer signals this condition variable saying, hey, there is something to consume, wake up and you can consume, right? So the producer waits on a full buffer, the consumer signals saying, I created some empty space for you. Similarly, the consumer waits on an empty buffer and the producer signals saying, hey, I have filled up some items for you. Okay, and for all of these wait and signal, there's always a mutex lock that is held and released, right? You must always hold a lock when you're either sleeping or waking up, and you can give this lock to the wait function so that it will release the lock. Then the guy will have the lock ready for signaling and he can signal, and then you get back the lock again. Okay, so always whenever you write code with condition variables, remember where should the waiting happen and put a wait function there, and who should wake up this waiting thread and put a signal function there.